We'll see.
That's a little extra.
I think you'll get used to it. All right. Right.
I appreciate that you said it with a smile and everything. Thank you.
Because I like you. All right. No, it's really because I like to feel like a pop singer or something. Who? Oh right, yeah. All right. Let's see. So you want to go over the right hand rule first? Yeah. I know it's sort of confusing to folks. So there are a couple of things. We have the palm rule. Right, and the palm rule, you're dealing with a couple different instances. That is F equals QVB and F equals ILB. All right. If you were in the 202, remember these were vector quantities, and we did the cross product between them. All right. So we let our fingers go in the direction of V. Our palm goes in the direction of B, and our thumb then gives the force. So for example, if I have a velocity vector here, a magnetic field vector here, I let my fingers go in the direction of V, like that. The magnetic field comes out of my palm, and then my thumb, which is into the page, gives the force. Right? So my force would be into the page there. Remember, if Q is negative, you just take the opposite. All right. Now, the same is for ILB. Fingers in the direction of L or I, however you want to think about it. Your palm in the direction of B, and then your thumb is in the direction of the force. All right. So if I have a current that is up and a magnetic field that is into the page, current fingers in the direction of I, the magnetic field comes out of your palm, so your hand would go like this because the magnetic field is into the page, and then so the force is to the left. Right, so here, the force would be to the left. Okay, that's the palm rule, and that comes in a couple different places. Like for example, with the mass spectrometer, right? We had a couple cases of this. If I have a charged particle plus Q moving into a magnetic field, say something like this, then I could ask you a variety of questions. I could ask you, for example, what is the direction that it's going to go, right? In a mass spectrometer, remember in a mass spectrometer, the magnetic field acts as a centripetal force, and that causes it to move in a circular path. And so, for example, here, taking our first application of the palm rule, V is in this direction, B is into the page, so the force is up. So this charged particle is going to follow a counterclockwise circular path in this mass spectrometer. All right. You also need to know, while we're on that, you need to know how a mass spectrometer works. That is that you give a charge a certain velocity, and you run it through a magnetic field, and then you measure the radius, and then from that you can find the mass to charge ratio. We worked through problems like that, and there was one on your homework as well. This is just based on the cyclotron equation, which actually comes about by this, QVB equals mv squared over r. That just says that the magnetic force is a centripetal force, and then you can solve this for r. This is on your equation sheet for all of you, and you can calculate then what r is for a mass spectrometer. Given a certain mass to charge ratio, you can identify the unknown particles. All right, I can send you these notes if you want over email. When you write it, I understand. Okay, well, I'm going to. Right, uh-huh. No, not always. So, I mean, you could have a magnetic field in a different direction. Right. But if the magnetic field is coming out of the page, then it would go in the other direction. You go clockwise, right? For B, you mean? That would be a negative Z direction. Yeah, typically when we have our X, Y, Z direction, Out of the page is positive z, and into the page is negative z.
So whenever we have all those sexes or all those points, we would just assume that automatically that's the field, right?
Right. Hmm. All right.
So you would say that the force is into the page, or the force will be up.
Hmm. Wait, on this one, the force is up for this one? Right, yeah. Well, right. Well, in this case, the magnetic force is a centripetal force, so it causes a circular path. And so here we'd get an upward force, and so it's going to pull this charged particle up, and that means, let me extend my magnetic field out here. You get the idea. The magnetic field is everywhere. And so then when this charged particle comes along here, it's going to feel a force pulling it up, and it's going to go into this circular path. Because that force will always be in this direction. You could go through and do the right-hand rule in all those different situations. It's always a centripetal force. It's always a center-seeking force. That's what centripetal means, right? Goodness, God bless you. Yeah, centripetal means center-seeking. Right? You will have to identify an unknown particle, like we did in class for all of you. Uh, you will have to apply the right-hand rule in this. I think there was also a problem where I had something like, I don't know, some charged particle like this, and I show you the path that it takes, and I ask you what magnetic field caused that. What magnetic field caused that path? Left, right, into the page, out of the page. Well, let's see. Out of the page. Yeah, it's just the opposite of this, right? Um,
At first, I didn't realize that it was going to a circular path, so that's why I got confused with your question. Whenever I started going down,
yeah, I think I remember that. Yeah.
right there,
Right here? Yeah, all you have here, no, you have force as well. It's just not labeled explicitly. Yeah, the force is down. Right, because it follows it's, I could just say this is the path that it takes. That's right. Yeah, so if it follows this curved path, that means that there's a force pulling it down. That's right. The vectors would look like this, but you wouldn't have this or this drawn on there. And I would just say, what is the magnetic field? And on this particular case, it's out of the page, I said, right? It's the opposite of what we had up here. But you can use your right-hand rule. F or V is in that direction. You have to turn your hand like this, and you have to do it like that. Right, with great confidence. And then the magnetic field comes out of the page, out of your palm. If the charge was negative, it would be into the page. I don't remember if I did any negative charges. I don't think that I did, but just make sure that you read them carefully. And if it is a negative charge, just take the opposite. Yeah. I don't remember. I'm sorry. I wasn't really listening. Go ahead. Let me answer another question. So if this was negative, and maybe this will answer your question. If this was a negative Q in this direction and following this path, you would say V, force is out, and then you would find, the magnetic field is out of the page. But since it's negative, the magnetic field is really into the page. Does that answer your question? Okay. All right. Let me show you the curl rule, and then we'll also look at a combination of the two. There are no parallel conductors. Forces, I mean, we didn't do it in your class. We skipped that, but for y'all too, there are no parallel conductors. Forces, it's just sort of an extra application. I know, that makes you feel good. All right, but the curl rule says this: if I have a current carrying wire, a wire with a current going in this direction, I let my thumb, this is my thumb right here, of my right hand go in the direction of the current, and then my fingers, there's my big finger right there, You'll get this? That's my hand wrapping around. Okay. That's my hand. Right, so you let your thumb go in the direction here, and then your fingers wrap around to give the magnetic field. Because anytime you have a current in a wire, it generates a magnetic field. All right, so here, the magnetic field is into the page over here and out of the page over here. Right? Sometimes you can draw, so that's your magnetic field. Sometimes your current carrying wire, say for example, looks like this. That's a wire coming out of the page, in which case you're not using the palm rule, you're using the curl rule. Your finger goes in the direction of I, and then your magnetic field oh, looks like that. All right?
So that's just another perspective of how to look at it.
Right. In this case, the wire itself is coming out of the page. Here, the wire was just going in the plane of the page.
So you can just look at it this way.
Right. hmm So the wire is coming out of the page. And then at any particular instance along this, your magnetic field is tangent to that circle. We saw that when we had a collection of wires together in the concept test. And you had to, right. hmm Right. hmm That's right. The tangent to the circle shows the vector, shows the magnetic field vector. All right. So I don't remember if there's a question like this, but it's a good question anyway. But I don't remember. It's been a while since I've written the test. So let's say that I have a wire right here that has a certain current in it, and then I have a positive charged particle that's moving in this direction. And when it gets close to the wire, it goes up like that. And I ask you, what is the direction of the current? I think there's a question like this on the old test, one of the old tests. There are two things here that you have to do, right? Two applications. First, you have to recognize, just forget about the wire for now, and ask yourself, what is the magnetic field that causes this to move in the direction that it is? Now look, it has a velocity in this direction and a force in this direction. And so this is just like one of the previous problems we had. Magnetic field is what? That's right. The magnetic field to cause this motion is into the page. Now, what kind of current in this wire will cause a magnetic field into the page? If it's up, it has to go down, right? The current has to go down because your finger in that direction, the magnetic field wraps around that wire and into the page, out of the page. So the current that generates this magnetic field has to be down. All right, so that's the curl rule, and this is sort of an application of both, where you have this charge that reacts to, a current in a wire, a magnetic field generated by a current. Okay, that's the curl rule. Okay. Okay. Yeah. I'll answer this, but there are no parallel conductors.
Yeah.
Okay. But this is still a good question. So, because it's just an application of the curl rule.
Because I thought that even though there were two separate wires, they would have the same, like, since both of them say going up,
Mm-hmm.
both of them would be in the same direction.
Okay, well, let's see. So here, the blue wire generates a magnetic field that's into the page, out of the page, like that. The red wire generates a magnetic field into the page, out of the page. All right, so in the middle here, when these two magnetic fields come together, they're equal but opposite. The magnetic field equals 0. As I said, there's no parallel conductors and no forces between parallel conductors like we've done in the class in 102. All right. Variety of another application of the curl rule. Let's say that we have a solenoid. A solenoid is a coil of wire, right, that looks like this. So let's say that there is a current going in that direction. Right? That means that the current flows in this direction Let me redraw it a little bit better so you can see it. Just make it a little more compact. Is that better? Okay, well, the current is coming in here and flowing in that direction and flowing up through the coil. Is that a clockwise? We're sort of looking at it, yeah, like this. All right? You'll follow it. This is a three-dimensional thing. This coil of wire stretches out like this, like a spring. All right? So I can figure out what is the direction of the magnetic field. I know the magnetic field has to either be up or down, right? Because I know that in a solenoid, that the magnetic field goes up either through the center or down through the center of the coil. All right, this is a coil of wire. Looks like this. The magnetic field goes through that coil in the solenoid. All right, so what is the direction here? Well, I let my finger go in the direction of the arrow. That's the current, which is sort of coming out of the page here. And so the magnetic field goes down, and then it comes back up on the outside. So if I were to draw the magnetic field, it would go down here and up like that. The current. Yeah, the direction of the current. Yeah, so like right here, well, here it comes out of the page using the curl rule. And so my fingers wrap around and they go down. No, this is the magnetic field. Right, that's B. Right. Magnetic force is F. This is supposed to be a 3D image, so it's kind of hard, but solenoid switches, you can. What's up, Jose? Mm-hmm. Right. Yeah, yeah, because like if I imagine this is just a wire coming out of the page, the current's gonna, or the magnetic field will go down in that direction, and then it'll curl back up again. Well, there's no force here because there's no charged particle to feel the force. Right. We're just finding the magnetic field. This is like over here. There's no force, right? Just magnetic field and current. All right? Because a current and a wire generates a magnetic field. All right? Now, if you're in the 202 class, make sure that you can do the cross product. You'll have a cross product. Remember, we had a couple different applications, the QV cross B and the IL cross B. Make sure you can find the vector L like we did in class. And those in 102, just make sure that you can. They're pretty basic, I think, the problems as far as finding the force or the magnetic field. Just make sure that you've practiced with those equations and that you know which equation goes to what. I give you all the equations, right? So it should be good to go. All right. Any questions about that? You want me to summarize chapter 6 as well? Let me think. Have I done everything for chapter 5? I think most of the equation stuff is pretty easy, but if we need to come back to it, we can. It's really just having practice with them, but we can come back and work through some problems in just a bit. But let me, solenoid, right? Solenoid. Yeah, solenoid switch like in your car. Or that British guy that we watched, that really cool British guy with the mutton chops or whatever. Every British guy is pretty cool, yeah. All right. Okay, so chapter 6 dealt with a couple things. Chapter 6, see for you 102 guys, it's there are 26 questions. It's like 18 and 8. Like 18 chapter 5 questions and like 8 chapter 6 questions. You need to know that history of light. Remember all those people? There was Newton, Huygens, Young, no relation.
Yeah, I asked you that last time.
Oh yeah, Young and Einstein. Right? Newton said light is a particle because of reflection. Huygens said that light was a wave because of refraction. Let me write these things down. So Newton, particle because of reflection. Huygens said it was a wave, that light was a wave because of refraction. Young said it was a wave because of interference, so a different reason. And then for a long time, people thought it was just a wave because the interference thing was a pretty big deal. We'll talk about it in a couple of chapters. And then Einstein sort of disrupted things. He said that it was a particle because of the photoelectric effect. All right, photoelectric effect. You just really need to know those sort of basic facts. No, well, actually, no, we're not going to see it again. But you might see it in your chem classes. Well, no, maybe not. Okay. Yeah. All right. So know this basic history. And then we had a couple of things. The law of reflection. Law of reflection is pretty easy. There's not a whole lot that I can ask. I mean, if I have a light ray that bounces off of a mirrored surface, this angle, theta I, will equal theta R. Really the most complicated thing that I could ask is bouncing off of, a couple different reflective surfaces. We work problems like this in class. Like say, for example, I don't know, this angle is 110 or whatever. I have a light ray that comes in here, say at 30 degrees. What is the final reflected angle? In order to do that, you'll just, oh, well, shoot, I'm going to run out of space. Let me make it bigger. Trace it out. If that's 30 degrees, this is 30 degrees. So this is, that's 60. Notice I have 60 and 110 is, no, 10 degrees. Right, they're 180 degrees in a triangle. That means the incident angle is 80 degrees, and so the reflected angle would be 80 degrees as well. You just need to know your triangles. All the angles add up to 180, and that's it. All right, law of reflection. Those should be easy ones for you, okay? And the history stuff too. They should be pretty straightforward. And then we have the law of refraction. Stop me if you have questions, okay? Is this okay for you? Just sort of reviewing it? All right. Law of refraction. Law of refraction comes in a couple different varieties. At its basic form, it just says that the speed of light is c over n. That is that light slows down when it enters a medium. You could see some basic kinematic stuff like we did before, like, what is the velocity of light in this medium, given a certain medium, and then, how long does it travel? Don't forget your v equals v over t kind of thing. And then also the law of refraction, when light enters a medium at an angle, you can say that n1 sine theta 1, and this is just a geometric argument based on this change in velocity. n1 sine theta 1 equals n2 sine theta 2. All right? You need to know how these indices are related to, like when we show a light bending in a particular way, what does that mean about the indices of refraction? So say, for example, I have a light ray that comes in like this, and when it refracts, it bends towards the normal. There are a couple things that I can say about N1 and N2. Or one thing, I can say that N2 is bigger or smaller than N1? Is bigger. If you ever forget, I always forget, so I always have to draw my wavefronts like this. And then I come up here and I imagine, oh, it's going to slow down here, and that's what causes it to sort of turn around like that. And when it comes past that transition, it's now moving in a new direction. And since it slowed down in N2, that means that N2 is bigger. All right. Another thing that you can say is that V2 is less than V1. All right. Remember that I have this inverse relationship between V and N. If N increases, V decreases. There were a variety of questions in the concept test regarding this and in our quick test too in class. So you'll see one or two questions like that as well. Just, what is the relationship between the n's or the velocities for these media? Uh-huh. I do too, Catherine. Yeah, I do too. So I sort of have to step through it every time. So if we had another situation like this, that's bending towards the normal. let's say that we have one that bends away from the normal like that. Imagine my wave fronts coming along here. Now, here, in order to get bending away from the normal, this is going to speed up. And that'll cause it, when it gets into this new medium, to bend in that way. All right? So as I'm traveling along my wavefront here, this part speeds up because it enters this medium that has a lower index of refraction. So here, this index would be less than this index. It's like you're in the mud. Here you're in the mud and you're walking onto the road. It's like that lawnmower video with Chris Cortez made. When his lawnmower was on the grass side went slower than the cement side, and so it caused it to go back and forth. In fact, that video, I don't know if y'all saw that. Y'all see it? Okay. It was in the screencast for that day. But it's a good example of total internal reflection, because that's really what's happening is the lawnmower is getting totally internally reflected. All right? A shoulder rule?
Yeah, because, if you go like this, then it's slowing down. If you go like this, it's speeding up.
I don't know. You should, I don't know, write paper or something. All right. Okay. There's several questions, but so this is the basic idea. It can't really get much more complicated than this. The only more complicated way to get is like the one we did in class, where we had 3 different media, like that, and you just had to apply that idea at each transition. Yeah. Do you want to look at some of those? Let's go ahead and finish this. Yeah. Is this useful for y'all? Okay. Now, a couple other things, and that is the internal reflection, total internal reflection. It's just a special case. N1 sine theta C is equal to N2 sine of 90. So if I have a, say, a glass core surrounded by air, I'm going to get light rays. If they come in at just the right angle, I'm going to get light rays that will come in and get totally internally reflected. And that critical angle, which is right here, theta C, is such that if it were refracted here, the angle would be 90 degrees. Right? So if just do this in one dimension, that glass, air, I can solve for this critical angle, taking the refracted angle equal to 90 degrees, just using this law of refraction. Remember, sine of 90, of course, is equal to 1. So it's like it's just N2 times 1, right? All right. You need to know the EM spectrum, right? It goes radio, microwaves, infrared, visible. Within the visible, going in this direction, it's Roy G. Biv. And then UV, X-rays, and gamma rays. All right, this is from high energy to low energy. I'm sorry, I got that backwards. Low energy, radio waves are very low energy to high energy. Gamma rays are very high energy, that's why they're damaging to us. This is long wavelength. This light wavelength on the order of kilometers for some radio waves, all the way up to very short wavelengths, like picometers. And radio waves have a very short frequency, or very small frequency, I'll call it low, up to a very high frequency. Right? Mainly know these wavelength and energy, how wavelength and energy are related for this electromagnetic spectrum. And then also realize that this is long wavelength, this is short wavelength. Red is long wavelength, like 800 nanometers. Blue is short wavelength, or 500 nanometers, I think. All right. And then finally, dispersion in prisms comes about because if we were to plot n versus lambda, it looks like this. And so on this end, which is short wavelength, that's blue light. On this end, it's red light. And so if I have a prism, I have light that comes in, and it's going to be broken into its colors. I'll have red that spent the least, blue that spent the most, because the index is higher for the blue light. Red is, it's around 700 nanometers or so. It's the long wavelength.
You will be saying that blue bends more proportionally?
Blue bends more because of this plot. The index of refraction is larger for blue light than it is for red light.
So it'll be the same thing. So you're not between that it will be going more forward.
Right. Yeah, so the normal line here would look like this. The red light is bent a little bit, the blue light is bent a lot. And then in between you get your orange, yellow, green, blue, indigo, violet. Something like that, yeah. It's less than red is the point. Whereabouts? Right here? Oh, this is lambda. This is the wavelength. Well, we didn't do waves in 102 and 101, did we? The wavelength of a wave? Yes or no wavelength? Right? Okay. All right. Right, I understand. Okay. All right. There's a lot of letters, I understand. All right. Let's do some examples. You said '08 has some good questions?
So actually, there's several questions that I want to know mine. But I think it's like number 18 on 2009, exam 2. There's another one just like this on more on other things. So yeah, I forgot that.
Yeah, which has the highest energy?
I think it's wrong.
Uh, oh, this is 2010, I'm sorry. Exam 2? Y'all have some multiple choice too. Yeah, I think the multiple choice is harder, honestly.
No, I just forgot.
E is your electric field.
When you say electric field, I guess like what the unit is it was D, I would say I was okay.
Mm-hmm.
I got it. But now like the velocity is my finger's gonna point towards the velocity, right?
Yeah,
Right hand pole?
forget about that right now. All right. So the point here is that you have an electric field that's drawn, and then you have another magnetic field that's not drawn. All right. And this particle is going to go through undeflected. So it has one force pulling it up and another force pulling it down. You have two things at play. You have an electric field and a magnetic field. Remember electric fields, chapter 2? An electric field will exert a force on a charged particle. F equals QE. I don't know if you remember that. All right, so you don't have to know how to calculate it, but you need to know that it exists. This electric field is down. The force on this negative particle is going to be opposite the electric field. All right, so Fe is always, for a negative particle, is opposite the electric field. So I have one force, Fe, that's up. That means I have to have another force, Fb, that's down. And then it becomes just like all the other problems. I have a negative particle. It's traveling with a velocity in this direction, and it experiences a force, Fb, that's down. And so we say V is to the right, magnetic force is down, so the magnetic field is out of the page, except that it's a negative particle, so it's into the page.
So the magnetic field.
Okay, this is the magnetic force, I labeled it FB, so this is an F with a subscript B, a little bitty b, but my pen's kind of fat, so F with a B subscript. This is the magnetic force. That's different from the magnetic field, which is just B. No, not necessarily. It depends. I mean, if this was a positive particle, the electric force would be down.
Oh, that's true. It would just be flipped.
Mm-hmm.
So we're not using the right hand rule in the
Not in the very beginning. At first, you just have to. Well, you have to determine. You have to ask yourself, what is the direction of the electric force? What is the direction of the electric force? And then you'll know that the magnetic force, FB, is opposite the electric force. Because you have this particle that's going to go through undeflected. It's going to follow a straight line. So it has one force pulling up and one force pulling down. This is like in old television. They have modulating electric and magnetic fields to deflect a stream of electrons in one direction or the other. And then they can change the electric field to make it go up or down, and change the magnetic field as well to make it go up or down. Well, let's see. So V is there. With the right-hand rule on this, you get out of the page, but it's a negative particle. Mm-hmm.
But also, because it's a negative particle, that's why it goes the opposite of the electric field.
That's right. So, right. Because it's electric particles in an electric field feel the force in the same direction as the electric field for positive particles. But negative particles feel a force in the opposite direction. If you remember, like if you have it's chapter 2, I think, or 3. 2. This first exam, yeah. That's already been dumped, I understand. Who, me?
No, I'm talking to him. How can you? I don't. That's what I'm saying.
Right, yeah. Okay. That's okay. You can dig it back up for the final, because it'll be on the final.
We're here already. Would the answer for number 19 be all these things?
I don't remember. Let's see. So, is that okay for 18?
Oh, one more question. So, uh, like you were saying, the negative particles of the electric field feel the force opposite of it was positive field of force in the same direction. So that would be positive. That would be pointing up.
If the particle was positive, Fe would be down,
That would be down, and that would be
would have to be up in order to make it go undeflected. Yes.
then you call that out as it was positive. FD would be up there, and then the FD would remain up.
Well, let's see. So,
That's right.
if it were positive, Fb would have to be up and Fe would be down, because a positive particle will feel an electric force in the same direction as the electric field. And so here, that's the electric field, yeah. I know this is very confusing, isn't it? All right. So this is FB. I don't recall if it's on the test, but I seem to remember that it might be. Um, no, not necessarily. I mean, they'll either be up or down.
So if you had your electric field line pointing up, and you had everything else remaining the same, your electric field would have to point down, because it has to go in the opposite direction.
Can you repeat that?
So like, if you had everything remaining the same except you drew, like on 18, everything was the same, except you drew your electric field line pointing upward. So those lines that are already drawn on the test would be pointing upward.
Mm-hmm.
You would have to draw your electric field in the opposite direction.
If the electric field, as you're saying, is in this direction, that's what you're saying? Okay, well, if your electric field is that way, then your electric force, Fe, would be down, and Fb would have to be up. And then you would want to find what magnetic field generates that force. And if it's still negative, yeah, that's assuming that it's still negative, but the electric fields are switched. Did that answer your question, Matt? All right. Unless my wife is able to stay, I'm going to have to leave at 3. She might be able to stay for me if y'all have additional questions. But Uh, okay, let me just, I'm gonna, yeah, you're not going to have that many. Like you might have one. Can I just do another example that takes less time? All right, so let's say, for example, you have two wires that are into the page like that. And I just ask you, I'm not saying this is on the test, right? I'm just making this up right here. And I just say, what is the magnetic field at that point? We'll call it P. All right. Now, make this one red. Both of these wires generate a magnetic field. They're into the page, so I use my curl rule. So the red one produces a magnetic field that is clockwise. And the blue one, likewise, because it's in the same direction, generates a magnetic field that is clockwise. And so at the point P, I get a vector in that direction, and I get a vector in, oops, I'm sorry. And from the blue wire, I get a vector, a magnetic field vector in that direction. So the net magnetic field is in that direction. All right, we did that before, like with the two parallel wires. They generated two magnetic fields, and you just add them up. A tangent. Yeah, so if I make these circles bigger, then I just draw a tangent line. All right, what else, folks? Now that takes forever. When you have like 12 wires or whatever, it takes too long for y'all. Right? Yeah, there are no forces between parallel conducting wires. Gosh, did I do? I don't think I did magnetic fields. I don't remember seeing any parallel lines. But y'all could do that, right? Just the magnetic field of two parallel wires?
Yeah, because
But no forces. Like, you remember there are forces in between them? I didn't put that on there. Right. Mm-hmm.
there's a combination one.
Out of the page here. Out of the page due to this one, too. You can see the current's in an opposite direction. So out here, it would be out of the page.
You know, I confuse myself by doing this.
Yeah, that's not right. Like, that's dance
Not
or whatever.
dance.
I think it's a dance. Like, I can dance.
Oh, if it was in the same direction.
Right. Mm-hmm.
Yeah, it would be fair. You get out to 11, number 14, number 12 as well, but I think number 14, 2011 is like exam 2, and number 14, it's one of those combo problems.
Yeah. Yeah, we did one very similar to.
Okay, sorry if that's wrong, I didn't have that label. Well, actually, and then I guess it was 2000, it's number 12.
I don't think I did number 12. Okay. No, I was joking. I was saying that there is no number 12 on this test. That's what I meant. But obviously there is a number 12. All right. Well, here. You don't need to use the curl rule on this. The only thing that you need to do is know the direction of the magnetic field. And in this case, it's not a wire that's generating a magnetic field. You have this permanent magnet that has a magnetic field that runs from north to south. So that is my magnetic field. It's a vector that goes in that direction. And my current is a vector that goes into the page. That's just looking at this side of the loop, at the right-hand side. You could do it for the other side as well if you wanted. It would have a magnetic field in that direction and a current out of the page. All right, and then if you want to know the force on this right-hand side, this part of the wire right here, current is into the page, so the force is down, right? The force pulls down here. Right. Likewise, you'll get an upward force over here. Right. Once it goes 180 degrees, the currents now are going in opposite directions from what they were initially. And so your forces are going to switch 180 degrees. So it'll go over, and then the forces will change, and it'll flip back over. Right. That's why in an electric motor, the armature, which is this coil of wire, you have to flip the direction of the current every half turn. Y'all hear me? The armature, you have to flip the direction of the current every half revolution. So it doesn't flip-flop like that. In whatever way that you do that, through AC electricity or by those switches that we talked about. All right? What else? Yeah. Yeah, of course. Okay, yeah. So, this is, mhm. Yeah, it's really simple though, because, I give you this angle right here, and I just want to know this angle. It looks complicated because it has these three media. You don't have to worry about this at all. It's like this doesn't even exist. It comes out just mathematically. I can say that n1 sine theta 1 equals n2 sine theta 2, right? That's the law of refraction. And then I can also say that n2 sine theta 2 equals n3 sine theta 3, right? That's also true. Like this relationship is true, but this one is also true. So if A equals B and B equals C, then A equals C. So I can say n1 sine theta 1 equals n3 sine theta 3. It's going to keep coming back. Wait till you take the MCAT. Yeah. Right. All right. And for what? No, if you go to grad school, you have to take the GRE. Pre-med, yeah. All right. And then you would solve this. So you would say N1, which is 1.4 sine of 30, equals 1.3 sine of theta 3. If you have trouble solving that, you really need to get some help with that. You can come see me. I think y'all are all okay. But yeah, if you were wanting to know this, instead of putting 1.3 here, you'd put what? 1.5, yeah. And this would be theta 2, right? You going to ask a question? Okay. No. All right. What else? I don't mean to rush out, but I want to get as much as I can. And if y'all really need to stay longer, my wife would probably go home. It's just my kids get off the bus. And one time I didn't get them off the bus. I still hear about it. It was like 2 years ago. It wasn't worth it. I thought the bus came at 3:30. It came at 3:15. Okay, what else? 2012. Yeah. 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 I forget. I've looked into this. I think maybe I was wrong in that. Can we forget 22? Okay. Um, hmm Now the 21 is not that difficult, right? You just say F equals. Right. I know. I can't think right now. What is the direction of the current? The reason is like I just imagine that there are these positive charges within the wire. So I have this positive Q moving through this magnetic field with a certain velocity, and then ask yourself, what is the force on that? But I think you maybe get a different answer if you approach it from a different way. So I haven't looked into that, why that is. B is what, out of the page? What did you say?
I mean, yeah,
I think it should be to the left. Was that the answer?
No. I'm looking. Okay, yeah, to the left. It goes to the left if you do that arrow as a velocity, but if you put that arrow as
It switches.
32
Yeah, I know it's spelled wrong. I know. I realized that recently. I'm doing something wrong there. I'm not sure what it is.
I don't know if you're doing. You're probably doing it right. I just.
No, I'm because you get two different answers.
As you move through the magnetic field.
I have to fix that. I don't know. I'm sorry. I just don't know. All right. I meant to look into it, but I forgot to. Hoping nobody'd ask. Thanks. All right. What else? Okay. Ferromagnetic doesn't mean that it's magnetic. It only means that it's able to be magnetized. Remember we talked about those magnetic domains, that everything has a magnetic domain, and these are like little regions within a material where the magnetic fields are all lined up. In a ferromagnetic material, those magnetic domains are able to be aligned. So like iron is ferromagnetic, but iron isn't necessarily magnetic, right? Like I can have a piece of iron and it's not magnetic at all. But if I bring it close to a magnet, the magnet will align the magnetic domains of that ferromagnetic material, iron. Ferro means ferrous, iron. Uh, right, right. Everything has magnetic domains. Like this wooden table has, or whatever it is, has magnetic domains. Formica, but it's not ferromagnetic. Right? It has magnetic domains, but you can't align those magnetic domains. So if I brought a big old magnet up next to it, it's not going to turn into a magnet. It's not going to be magnetized. But it's able to be magnetized was what ferromagnetic means.
So why do you have to have molten iron?
Because when you have molten iron and then it cools, those magnetic domains get locked into place. And so then your iron becomes a permanent magnet, right? Because it cooled while the magnetic domains were aligned, and then when it cools, they get locked into place, like at a atomic level.
They get set into a set direction.
Right. They're all set in the same direction. Okay. What else? Okay. It's actually 3:30. It comes. I think 3:30. I was at the house when the bus came. I was inside the house. Huh? Right. Yeah. Every time I hit, my boy's like, "Daddy, don't forget the bus comes at blah blah blah." Dude, that was like 2 years ago. Yeah.
No, don't worry. You got it on recording. You thought it was 3:30. We know.
Right. Right. Okay. Is that all then? All right. As soon as I stop this, I'll give you all the answers.